Hello everyone. So in this video, I will be mainly explaining the Laplace domain and the S-plane mainly, the S domain. And why poles before -1, that is, when we have poles at this side, the system is stable. When we have poles at this particular part, why it is marginally stable, and when we have poles at the right side, why the system is unstable. So that will be my aim for this video. And in order to explain that, I'd like to also explain about the origin of the Laplace transform as well. Not the transforms formula, but how e raised to st was originated. So for that, we first must understand Euler's, or just let's brush up Euler's formula, e raised to j over j theta, which is cos theta plus j sine theta. So we know that this particular formula produces mainly sustained oscillations. But now EST on the other hand, where S is the real part plus again the same, this only. This allows an additional flexibility into the oscillations. That is, with e raised to st, we can define a rising oscillation or a decaying oscillation. So that's the flexibility we are given with. That's the flexibility Laplace had added. And this mainly originated because, differential equations, like let's take an example of a simple one. Now, this, as we all might know, is a natural response of a system. We learned this in the NAS subject, actually. There's natural, there's also forced, but forced isn't our concern right now. So typically for these types of systems, we need to find y so that we can really determine how the system will behave for various values of t. Now the problem here is that for this thing to become 0, many things were tried for y. Like for example, they tried a straight line, they tried various other, they tried 2t, then t raised to 2, t square that is, and none of them really gave 0. So somebody tried this particular formula or expression. And the amazing thing about this is that this is an eigen function, which means that after being differentiated, it retains this, and only a coefficient is added depending on the power. Why this was revolutionary was because no matter how many of these terms you had, your entire calculus equation would ultimately become algebra of this kind equal to 0. And this algebra would ultimately be so easy to solve that engineering would just explode. Now, this equation is actually very familiar to us because we know what we do next about this. We find the solution for this. So the solution of this will be this particular thing. Now I'm not done yet with the solution, obviously. Now, uh, what we need to do here is find the value of z such that this expression will be 0. One thing about this exponential is that it is never 0, for reasons that I'm still learning. But To find solution of this, we simply equate this to 0. This is pretty familiar to us, as we all know. That's all we did in the control system subject, where we had the characteristic equation equated to 0. This is exactly the reason why we equate it to 0 and find S. Our main aim is just to obtain solutions for this particular thing, the natural response, that is. So again, the value of this will be -2. And what does this mean? Our solution of this particular equation is nothing but e raised to minus 2t. So this particular expression will give us how our system will behave for various values of t starting from the origin. So it will be again a decaying exponential, obviously. And this thing, when applied to larger ones, it really simplifies solution finding. So here I've written an example as well to tell how differential equations are converted to algebra. Here, solving this would take a long time, but with e raised to st, this Laplace constant, I'd say. I'm not sure if this is called as a Laplace constant or not, but this literally converts your thing to algebra, because uh, differentiating raised to st is this, and then 3 divided by dt is this, 2y is this, and this, when taken common, is quite literally a quadratic equation. And what are its roots? It's -1 and -2, and what does this indicate? E raised to t plus e raised to 2t is your description of the system, of this particular system. That's again quite amazing. We could stop here, and because we have found how our system will work based on the inputs, based on rather how it naturally behaves. But now here, when we do analysis, here comes S-plane. Let's firstly see what an S-plane is. So S-plane is where the x-axis is a real value, that is from this thing, the real value, and this is the imaginary value. Now, as per my understanding so far, I'd call an S-plane an indicative plane, mainly because it's not a direct plot of some or system's output, but rather it is an indication of the oscillatory behavior of your system output. Now, what do I mean by that? So for this, I'll take the help of MATLAB actually, and also simulate various values of this thing, that is various values of points here. So before explaining why systems here are stable, marginally stable, and here unstable, let's first understand how oscillation happens here. So let's take e raised to st equals e raised to the real part but plus e raised to your j omega. This is really nothing but Euler's formula plus that added constant. So what this means is that this is an oscillation. What this means is that it is either rising or a falling value or decaying value. So one thing seen about this is that when we have, let's first, so this is clear. Now let's take a value somewhere around here. Let's say we have, let's say you have e raised to 1 plus 0 rather 0 plus 1j. And let's try to simulate it in MATLAB. So I've come to Octave here because I didn't have MATLAB. Firstly, I've defined a time series with this step. This is a continuous time series going till 10. I've chosen this value from a previous simulation. 10 gives us the full picture. Now let's define the function. So we had e raised to so this will be e raised to 0 plus 1j, which will be multiplied by t. And if we hit on run, we'll see nothing but an oscillation. And if we want to see a bigger picture of this, let's change it to 30. So another figure just popped up. And yeah, this is a sustained oscillation. So any point in this lying in this j omega axis will be a sustained oscillation. Now, what does the imaginary value indicate? Imaginary value indicates how fast that oscillation is occurring. Nothing much. So we can also see it quickly actually. For example, if we change this to 4, then we'll see a higher oscillation. So what this really implies is that this is near to DC. This is a higher oscillation. This part will be an even higher oscillation, and this part will be astronomically high. And the same is true here. Here, because the frequency is reversed, so it will probably start from the reverse. It will have a reverse start. Just like how in Fourier transforms, we have reverse frequencies as well, negative ones. So this is what the j omega axis indicates about system's oscillatory behavior. Now, if we modify the real part as per my observation is nothing but how fast that rise and how fast that decay occurs of that oscillation. This can already tell an answer why poles here are unstable for unstable systems and why poles here are for stable systems. Rising means again output is uncontrollably high. So it is an unstable system, but here outputs are decaying to a stable value. That's why they are called stable systems. And we shall also see this with the example of MATLAB, obviously. So herein I will quickly write this expression in MATLAB. That is, I'm defining a point somewhere around here. And I've added the changes here. So herein it indicates that it will decay and it will have a rather slow oscillation or rather slow rise. And yeah, it is quite gradual. It does decay, but to indicate it better, let's try increasing the frequency. And this gives us a greater idea. So we can see that the oscillation is decaying and it is now zeroed. So this is a stable system's pole. Now what if we have a pole at the right side? The pole at the right side creates a rising oscillation that is indicative that the output can be uncontrollably unstable. In fact, the value reaches to e raised to 13, which is an astronomically high value. So this gives us a beautiful explanation as to why we have stable systems here and unstable systems here. So to quickly draw a good graph here, this is the illustration and the essence of the S plane. I hope this video was correct and also informational. Thank you for watching.